We did the introduction. Now we're going to start looking at the actual meaty parts of this and how to use all those graphs and things that we played with in the last video. Let's just take a step. Momentum. Now, momentum is it's a term which is very often misused. Like energy is very often misused as well. Power is very often misused. In physics, and I can only ask you, please talk in the language of the subject. So try and use power when you mean power, okay? Momentum when you mean momentum. It just helps so that you're clarifying what you're talking about in essence, doesn't it? Let's look at momentum. Something I call this, and a hint is, you're either going to get the boom or the bash. In other words, something's exploding or something is crashing into another thing. So we've got, in essence, two things. We've got a boom and we've got a bash. Okay? The boom and the bash. So in the boom, okay, stuff explodes apart. Okay? And in a bash, we've got, as I like to call it, stuff hits stuff. Okay? So stuff is hitting stuff. Right, that's cool. Now, what are we looking at? What do I mean by boom? Well, let's take, for example, if we've got two vehicles, right? Here they are. Here's two trolleys. I'm just using them as two cars. And they are together like this with a spring between them, right? Then we've got a little lever and we flick the spring and the spring explodes the two cars apart, okay? That's my sort of explosion or a boom kind of thing. The other one we're going to talk about is the one I like, is the astronaut problem, floating up in space with a tank full of gas. If you've seen the movie, I think it was Gravity. Yeah, I think so. If you look at that movie, Sandra Bullock was in it and George Clooney, I think. You'll see that they also use those little gas tanks to propel themselves around in outer space, right? So we've got those two things. The other one is we've got things that crash into each other. The sports car going from behind, bang, hits this car. Now, if they hit, two things can happen, right? They stick together as a wreck and they float off as a wreck combined, so they squish together. The other one is that they could, for example, bang like that. This one could stop and this one go backwards, or this one could go backwards, right? Or this one could hit it and stop. So we've got options, right? We've got them hitting and both moving off together, or we've got them hitting and then splitting apart again, all right? Now, let's just go through some definitions here. Momentum. Momentum is this. Momentum is, yeah, guys, okay. Momentum we define as P is equal to mass times velocity. Mass times velocity. Let's have a look at the units. Mass is kilograms, velocity meters per second. So our units for this guy are going to be kilogram meters per second, or in the old way, kilogram meters over second. Please, when I use them interchangeably. It's just something that I do. So we've got that, okay? Now, thus anything that has movement has got momentum, okay? Because it's got a mass. That is a planet is moving, it's got a momentum. I know it's spinning, it's called angular momentum. We don't do that here, okay? We'll be doing that in university or A-levels. Now, let's have a look and say, right, that. But hold on, an electron has also got momentum. Why? Well, electron is very tiny. It's got a very small mass, but an electron is moving at quite large speeds, isn't it? So everything has got a mass, okay? Rather, everything that's got a mass and is moving has got momentum, okay? So that's important that we just get that out the way, because if you suddenly see them talking about electrons or atoms or molecules, same thing, it's got a mass and a velocity, right? Right, cool. Now, let's have a look. When stuff explodes or crashes, okay, we get what's called delta P. Delta means change. Change in P, change in momentum, which is going to be mass times, or let me just do it this way, shall I? Okay, P final minus P initial. Why did I write final minus initial? Because that's what we do, okay? That's what we do in physics. We write final minus initial, okay? So it's just a process that we're going to stick with and we're going to go through like that. So when we do velocity, it's velocity final minus velocity initial. Those of you who started on the earlier years with me, you'll see that we hammer that point a lot, okay? So let's have a look here. We've got that. Now, change in momentum is final minus initial, which is mass times velocity final minus mass times velocity initial, correct? Which is, mass is a common factor, Vf minus V initial, which you could also say is m times delta V, correct? If you really wanted to. The next thing is, please note that momentum is a vector. Why? Well, we just said momentum, a vector has got magnitude, the scalar, and the direction. We said this car hits this car. Poor guy driving the Lambo, but he hits this car, okay? Now, he's got a velocity and he's going that way, because if they come together like this, this one is going in this direction, this is going this way, the momentums are in opposite directions. Where most of the students go wrong is they forget to assign a direction. We're going to do the recipe now, where I'm going to tell you, please assign a direction, okay? You don't have to be anal, but just remember to do it. Say to yourself, I've got a direction, I'm going to assign this way as positive. And tell them, tell the person who's going to be marking this which way is positive. Don't let them guess, because why? When the person's marked 50 papers, they've kind of had enough of trying to guess what you're trying to do, okay? If you're straight up front, say this is positive, that's, do you know what? It becomes a pleasure for anybody to look through, doesn't it? Right, so let's go this way. So, okay, we've got that. Now, momentum vector, we've done that, left or right. Next, we're going to discuss the term of impulse, okay? An impulse, no, this is not an impulse purchase. Impulse, okay? Impulse is a force acting for a length of time. You must do your definition straight out of your textbooks. A force acting for a length of time. And impulse is equal to J, which is equal to F times delta T. All right? Now let's have a look at this. What are the units of this guy now? F delta T is going to be equal to newtons, okay, times seconds, okay? But hold on, Newton isn't a base unit, is it? Newton is equal to m times a times seconds. Mass is kilograms, acceleration meters per second squared times second, which is kilogram meters per second, which is equal to kilogram meters second. Can you see that the unit of change in momentum, okay, the change in momentum unit is kilogram meters per second. So have a look here now, all right? Oh, our first new color change, right? There we go. Okay, it is the same. It's the same unit, guys. So change in momentum is equal to impulse, right? P is equal to J. Pretty cool. But why? That's important, because now we've got another formula that we can use for all of this, isn't it? We've got another approach, if you like. Let's go back to our black pen. So therefore, change in momentum, change in momentum equals impulse. Therefore, I'm just going to put here delta P, delta P must equal, I'm going to use impulse. If your teacher wants to use J, that is also cool. So now we're going to say, okay, kilogram meters per second. And I'm going to say, therefore, delta P is equal to F delta T, right? Therefore, F is equal to delta P over delta T, which is mass times V final minus V initial over delta T. And this is important to understand, to know. And guess what? We're going to look at a couple of examples using these kinds of things. You know, it involves when you're playing tennis, you're told, or cricket or golf, follow through, right? In other words, what are you doing? You're maximizing the time of contact between, because your arm, no matter, you can work out, right? But you've got a limit to the amount of force F that you can apply, okay? You can apply only so many newtons to that ball. How do you then get it to go faster? You make sure your contact time is increased. We'll have a look at it now, all right? Let's just see here. Oh yeah, that's exactly it. But what are we saying? We keep the bat in contact with the ball for longer periods of time, all right? We say here F times delta T times delta T is equal to M times delta V, right? Now you know that the mass of the ball is a constant, right? Your force is a constant. You can't go higher than so much. So therefore, F delta T over M is equal to change in velocity, correct? If I want that to be high, what do? The force and the mass are constant. I must change my contact time, right? This is our contact time. Okay, so if I up that, I'm going to get a higher velocity, aren't I? So I am increasing this side, which means my velocity final is going to be higher. Okay, just think up your own example. Pick a force, 100 newtons, mass, a cricket ball, what's it, 185 grams, call it that. Remember, just be careful. Remember physics, kilograms, meters, seconds, right? Put everything into those. That's critical. Total critical import that we do that. Okay, let's put another page here and take it back to a black. Now, what else? Oh, hang on. Seat belts, okay, airbags, etc. When you're traveling in a car, okay, my favorite pet hate, it's even one of the videos on my site, is people with their little toddler in the front and they're traveling along and they're bouncing the little character up and down and then suddenly they have to hit brakes. Everybody thinks, oh my goodness, I can hold on to my child. No, you can't. Your child will become a projectile and your child will hit something very hard. And because it's a very young child, the chances of serious injury or even death occurring is huge. And I know, you know, we're never going to stop people from doing it, but hey, if through this we can get one person to stop, I'm sure it'll be great. And I mean, you know, people even think that in a parking area, traveling slowly, yes, the problem is when you hit something, your first instinct isn't to grab the child. Your first instinct is panic. That microsecond of panic, the child is gone out of your hands. You know, children sitting on the back of a vehicle. They're traveling at the same speed of the vehicle. Right. So let's have a look. Yes, we reduce the force. We have crumple zones. This is just a bit of text. Okay. I've seen it come up time and again in exam questions. Okay. There was even one a couple of years ago, quite a long, very nice question about graphs showing the differences, hitting barriers and things like that. A really good question. All they're asking is a bit of theory. All you're doing here is you are basically increasing the time that you are in contact with the airbag. So you are reducing the force on your body as the velocity changes. Remember, The velocity change is a given in this case, right? That's a given. The F rather the delta T is a variable. So we're trying to reduce the force on the human body. Okay, our bodies are not that well equipped to handle the forces. It's not our bag, so we've invented airbags. Okay, now the last thing is this: is conservation of momentum. I'd like a drum roll because we are so happy when we see this word, aren't we? Conservation of momentum. Right? Everything is conserved. Please, you will be asked the definitions. I know, I'm a pain. I keep saying it, but you will be asked. Why not just learn them? I know there's quite a lot to learn, but just learn it. You'll be asked it. But essentially, what's it saying? It's saying that the momentum before is equal to the momentum after. Okay? That's what this is about, right? So we say, okay, momentum before equals momentum after. The actual thingy is, it's the conservation of linear. Now, what am I talking about here? Linear momentum. What am I saying? Linear momentum is quite straightforward. Sorry, I've got it. Okay, linear momentum. It means linear, it's in that line. So if my vehicle is moving that way, momentum is conserved in this direction. That line. If we are moving this way, up, down, then it means the momentum in this direction is conserved. Okay, so the mass times velocity in the up or the sideways or any other direction of a line is conserved. Okay, essentially, once again, what we're saying here is when we do the next step, we're going to see that angular momentum is conserved, right? You can get momentum in two directions. Just give an example, okay? This one is not currently in the syllabus, but if I had a truck moving that way and a car moving that way, M1, V1, M2, V2, they hit each other and they move off that way as a wreck. The conservation of momentum in this direction is conserved, and the conservation of momentum in that direction is conserved, and the conservation of momentum in this direction is conserved. Okay, we're not going to do those. All right, we're keeping it in one direction, and we're only going to deal with it in a single direction. Let's move along with a little bit of this. Okay, we're just going through the theory at the moment. All right, now the key to momentum calculations, right? The key to it is understand that we're talking about that impulse has got this delta t, right? It's a small increment of time, all right? When we have got this collision happening here, like this, the delta t we're talking about is this split second when that and that collide. The momentum is transferred and equalized between the units. I'll explain how we're going to calculate in a moment. But please understand that the delta t is an increment of time. If I have got a block here, and another favorite one is the arrow in the block, which is momentum and energy tied together, that just at this point of impact, right, it's momentum of this, momentum of that is the initial of these two. Then afterwards, it's the momentum of the combined bodies because they are together. Remember I spoke about stuff hitting and going off together or stuff bouncing off each other. Okay? Very important that when you read the problem, you look and see what they say. Okay? That's critical. Now, let's have a look. Okay? Collision. Okay, do that. All right. Just before we go a little further, let's look at something. Whoops, sorry. Let's look at this. It always gets my eyes when it bounces like that. Elastic collision. Elastic collision. What is an elastic collision versus an inelastic. Inelastic collision. What's the difference? What are we talking about here? We're saying that an elastic and an inelastic collision. An elastic collision is generally between two. I like to tell students it's essentially between those. You know, you get those super balls, the very, very squished, bouncy ones that you drop and they bounce virtually to the same height. That's elastic. Snooker balls, okay? Generally elastic collisions, right? What it means is it's the conservation of energy. Okay, elastic is the energy is conserved. And because it's movement, it must be the kinetic energy is conserved, right? And if EK is conserved, it means that a half m, whoops, let's just make that a little tidier, okay? A half mv squared is conserved. In other words, on an elastic collision, and I'm drawing it under the inelastic section now, maybe I'll just take this one out the way quickly. What are we saying? We're saying that, just make this look better, whoops, get you out the way. So we're saying here that if I've got something, and something else colliding, and the collision is elastic, okay, it means that EK initial and EK final are the same, right? So that means that the energies are the same, okay? Right, then we say, right, in inelastic, all right? Inelastic, on an inelastic collision, EK is not conserved. Not conserved, okay? What do I mean by that again? Well, it means that the EK before is equal to the EK after plus losses, okay? Sound, heat, deformation, etc. Let's just look. Sound, heat, deformation. Okay, what do I mean by that? Why? Deformation, because it takes energy to crinkle something up, doesn't it? To bend and buckle metal takes an energy that you have to apply. So the energy is absorbed by those things. Airbag, yeah, the energy is absorbed by that. Right, now, essentially in this type of problem, all right, we're doing very well over here. Next one is my next page. Okay, page 2, page 3. Okay, cool. Now, we've got 3 types of problems, okay? So there are 3 types of problem here. 3 types of problem, all right? There's the collision. I call it the boom, okay? Which is, let's do explosion first. Explosion, where you've got 2 objects that are sitting like this, and we have got a spring. Or, okay, you have an object which is flying along here like this, and all of a sudden this thing explodes, and this is before, and then all of a sudden this piece goes that way, a piece goes this way, and a piece goes off like that. This explodes over here. All right, like that. So that's our explosion types, all right? So it's very straightforward, okay? Then you've got your normal bash, okay? Bash, which is a collision, all right? And that's quite straightforward, okay? They will tell you 2 vehicles collide. Then you have got an, I'm going to call it mass altered. Mass alteration. Okay, this is a different type. Essentially what I've got here, mass alteration, is something, here's my, whoops, sorry guys, here's my little, whatever it is, it's on wheels, and it's moving that way. So I've got that moving that way. It's got a mass 1, and it's moving with V1. And as it passes a point, I drop another mass on it. This is M2, M1, and you have to work out what V2 is. What has happened here? Quite straightforward. The mass, this has moved, and as it moves past, you drop something on it. What's going to happen? Logically, it's going to slow down, isn't it? Yeah, that's what you see in real life, right? This kind of thing is where you've got, for example, coal trucks. They come in under silos, all right? And then suddenly they get filled, okay? Or a silo empties grain. Or suddenly water's taken out of the back of it. Then it will speed up. These are real life situations where you have to look at it. For example, if you're an aeroplane and you're flying along and you're carrying this tons of water, and all of a sudden you open the doors and you drop the water onto a fire, a bushfire, right? That's your job. What's going to happen? All of a sudden, your mass might have gone down by half. Okay, what happens? Your velocity is going to increase, isn't it? So those are real life situations that we've got to take into account. Okay, right. Now then, the last bit before we do examples, which will be on momentum 2, the last bit is the recipe. Okay, I shouldn't have to say, but I mean, you've got this, you take notes and whatever. The recipe, okay. In physics, what do we always do? What do we always do in physics? Step number 1, draw it. Draw it, draw it, draw it. It will make your life so much easier if you draw it. I promise you this. Okay? I know drawing little cars and whatever can be seen as very puerile, but we're trying to get the marks here. We're not really trying to impress anybody. We're trying to understand what we're doing. We need to draw it. Okay? It's not mathematics where we've got equations. Okay? Many people like to put it that or into that same vein. I don't. Okay? Because I don't believe that you can keep the image of something coming along and exploding in your head and then doing the calculations without destroying, drawing it. So step 1, we draw it, okay? And you draw the before and, after. Okay? So you do your little drawing of before, this one, over here, okay? Put in the mass, the velocities, put in the direction. Okay, critical. And which way is positive? Okay, that's all you need to know, because otherwise, if you get it the other way, it's going to be negative, correct? Right, so we draw it, okay? And label it with the given stuff, mass, velocity, etc. And then you say to yourself, okay, if they talk about elastic or inelastic, elastic means energy conserved. Okay, that is step 1. Okay, step 2, calculate P initial, okay, and P final, okay. And step 3 is going to be step 3, put P initial equal to P final and calculate the unknown. Okay, that is what you do essentially. Okay, so what do? We say, okay, we draw it and we put the directions in. We're going to do 5 examples in the next video, but you put the direction in. So if it's 2 snooker balls coming at each other, you put them in. If it's 2 vehicles, one behind, draw them and put in the velocities and the masses. Okay, then draw the aftermath, because they could tell you that the wreck, or in other words, they join and continue, or whatever. That is telling you that after it, you would draw that car A and car B are together. Important. Why? Because it's now mass of A plus mass of B when you calculate final momentum. Okay? Very simple, very straightforward. Critical that we do that. Okay? The next step, yep, when you've done that, you've got your directions. Because why? Because if I have got a ball of mass of, let's say, 5 kilograms, traveling at 5 meters per second that way, it has got a mass of 25 kilogram meters per second. And I have a ball of 3 kilograms traveling at 10 meters per second that way. It's got a P equal to 30, but minus 30 kilogram meters per second, or kg ms minus 1. Okay? Minus why? Because this is my positive direction. That is where most of the errors occur in these types of problems. Okay, in the next one, in momentum 2, we're going to go and we're going to solve, I've got 5 different types of problems, and we're going to go solve those. Look forward to seeing you then, okay? And remember, in physics, draw the problem. We're going to say that a lot. Deal with it. Cheers. Have a good one. Bye.